All right, so in this video, we're going to look at the general process for trig substitution. Trig substitution is generally used to evaluate integrals that have squared terms under the radical. So 1 minus x squared, or x squared minus 1, or as we'll see with tangent, 1 plus x squared, or some constant plus x squared. Now, I try to remember which rules go with which by remembering the arc secant and arc sine and regular derivatives. So if you take the derivative of arc sine, you get this 1 over the square root of 1 minus x squared. That reminds me that when I do a sine substitution, I'm looking at radicals that have this form, 1 minus x squared. And arc secant, the derivative is 1 over x times the square root of x squared minus 1. That sequencing x squared minus 1, not the reverse. That's what's going to remind me that this is a secant substitution. And then the derivative of arc tangent is 1 over 1 plus x squared with no radical. But that sum of squares in the denominator is what's again reminding me that if I see that sum of squares under a radical, that's a tangent substitution. And these substitutions are going to depend on that Pythagorean identity that we're going to use in order to simplify the radical once we've made our substitutions. So in general, our substitutions are going to take 3 general forms. If the radical form is of a constant minus a function squared, and this might be x, or it might be x squared, or it might be e to the x, again, it depends on what particular problem you're doing, you will replace that function with a sine theta, where a is related to this constant. That's what's going to allow us to pull that constant out of the radical and apply our trig substitution. If the radical has a sum of squares under it, then again, a constant squared and a function squared, then we're going to substitute for that function with a tangent theta. And if the radical is of the form function squared minus the constant, then we substitute for that function with a secant theta. All right, so these are our general principles. So what we're going to do is we're going to go through and we're going to do one example each. One sine substitution, one tangent substitution, one secant example. The thing to kind of keep in mind, I've noticed particularly with the tangent substitutions, if your radical turns out to be in the numerator, when you convert all of this to trig functions, sometimes you get you get integrals that are very unfun to integrate. Most of these others don't blow up quite so badly, but this is the one where if this is in the denominator, it's not going to be too bad. But if you've got a lot of powers of x in the numerator, you might be in trouble in terms of the back end. But the procedure works the same way. We're going to convert these to trigonometric integrals, do the integration, and then we will have to go back. And the going back to the original function variable is where sometimes people get into the most trouble. So we're going to talk about that as we go. Now we're going to start out with a very simple example involving just the radical, 1 over the square root of 1 minus x squared. We actually know what this is because this is a basic rule. And in general, I would not recommend that you do trig substitution for something that you can integrate with just a basic rule. But I thought it would be useful to see that, like, if you do trig substitution, you are going to get the same answer that you would get by using the basic rule. And it gives us a way to look at the procedure. All right, so we have this integral, and we know that because this is a 1 minus function squared, a constant squared minus a function squared, that's going to be our sine substitution. Our a squared here is 1. That means a is 1. And we just have x squared here, so our function is x. And so we're going to let x equal sine theta, 1 sine theta. Now, when I take the derivative of this to get my dx, then this will be dx will be cosine theta, because the derivative of sine theta is cosine theta. And I can substitute my sine theta into x squared here in my radical. I sometimes recommend to students that you do these simplification steps outside the radical and then just plug in everything after you've simplified. It's a little less writing. But here I've just substituted directly into the integral. I've replaced my dx with cosine theta d theta, and I replaced my x here with sine theta, and I get this. By using the Pythagorean identity and solving for 1 minus sine squared theta, I can replace this entire expression with cosine squared theta, and then the radical and the square will cancel and leave me with just cosine theta. Now, this is, I want to stress to you, to make this easier, this is always going to happen. So if you that's the whole point of the trig substitution. If you replace your function with sine, then your radical is going to reduce from your substitution of a sine theta. Your radical will always turn into a cosine theta. And we'll see this happen again in the other substitution forms. If you make a substitution for tangent, the radical will reduce to secant. Again, a tangent will become a secant. And then if you substitute for a secant, your radical will turn into a tangent. That is sort of the point here. So that can sometimes help you with your simplification process, so you don't have to show as much work. I recommend working it out a couple of times yourself to make sure that this is obvious to you, but it is what is inevitably going to happen. Once you get to this point and your radicals are gone, then you can work your trig functions. In this particular case, because it's a nice simple one, you can just cancel your cosine functions, and then you just end up, you're integrating 1, which turns into a theta. Now, whenever you're doing trig substitution, you have to go back to the original variable. And so if I solve my original substitution here, x equals sine theta for theta, then I get theta is equal to arc sine x, or inverse sine x, and then I just substitute that into my answer here, and I get arc sine x plus c. And that's exactly what we should have gotten from just using a basic rule. So even though I don't recommend ever really doing this if it's just a basic rule, if you don't happen to notice that it's a basic rule and you just kind of plow ahead, you will get the same answer that you would have gotten. It'll just take you longer to get there. All right, so let us look at another example using another version of this. So this one is a tangent substitution because we have a sum of squares under the radical. So in this particular case, again, we can't do this by traditional substitution. If this was just an x in the numerator, this would just be a regular u sub, but it's not an x. It's something other than an x. It's an x cubed in this case. And so what we're going to do is we're going to try to do trig substitution on it. It is possible that this could be done by integration by parts, by taking x over the radical as one function and integrating it, and then having x squared as your u function. I think you could do that, but we're using it as an illustration of trig substitution. Integration by parts in this example would be very dependent on what exactly the power of x is. And you don't have to worry about that when you're doing this by trig substitution. So our a squared is 4. That means a is 2. And our function again is x. And so we're going to let x be equal to 2 tangent theta. The derivative of that is 2 secant squared theta. That's for replacing this guy. And then again, the radical, if you replace your 4 tangent, your x squared with 2 tangent theta, you're going to square it. That's going to get you 4 tangent squared theta. Then take out the 4. The square root of 4 is 2. And that's going to give you 1 plus tangent squared, which will turn the radical into a secant squared. And then the radical and the secant will cancel. And that radical will again turn into 2 secant theta because our substitution was 2 tangent theta. So again, that same process is in mind. And in the numerator, we're replacing x cubed with our 2 tangent theta quantity cubed. So that's our 8 tangent cubed. This is our dx, and then this is our radical. And if we simplify a bit more, we're combining our 8 with the 2 from our derivative. That's getting us 16. In the denominator, I'm continuing to simplify, and I get it down to 2 secant theta. My 16 and my 2 can reduce, and my secant here can reduce with my 1 secant that's up top, and I end up with this. Now, this is a case of odd tangents. And so for the case of odd tangents, we would pull out 1 secant and 1 tangent as our derivative. And then the remaining 2 tangents, tangent squared, we can convert to secants by using our Pythagorean identity. So secant tangent, and then the tangent squareds become secant squared minus 1. I pulled the 8 outside the integral. This is our du, secant squared tangent, our secant tangent. And so that means our u substitution is secant. And then to integrate, this will simplify to u squared minus 1. And this will just be du. And so now all we have is a power rule, u cubed over 3 minus u. But we're not done because we have to go back to our original variable. So the u's get replaced with secants. And now we have this expression, but we're still not done because now we have to go back to x. X was the original variable. And so we have to go back to x. So in our original problem, we saw that because we substituted x was 2 tangent theta, this radical that we started with reduced to 2 secant theta. We can actually use that solving for tangent theta, or solving for secant theta to do our substitutions, or we can build a triangle. So here's our triangle. Originally, we started out with 2 tangent theta is equal to x. We solve for tangent theta, we get x over 2. Remember that tangent is opposite over adjacent. So here's our triangle, here's our theta, opposite side is x, adjacent side is 2. What does that make the missing side? Using the Pythagorean theorem, we get this square root of a squared plus b squared. Well, this is, as I noted, just the radical that we had in the original problem. And secant of this angle is this radical over 2. So that is just solving this, when we simplified that square root, we got 2 secant theta. If we set that radical equal to 2 secant theta, solving for secant theta, we get the same thing as we got out of this triangle. And then we simply replace this expression for secant into our expression that we got up here. Everywhere there's a secant, we replace it with this expression. And so we end up with our coefficient, 8/3. This was our secant. It's being cubed, minus 8. Again, distributing that 8 through the whole expression. This, we had 1 secant here, and then our constant. Now, one important thing to note is that occasionally, particularly with the sine and cosines, you will have to do like power reducing identities or things like that in order to get to the problem, in order to get through the integration. You're going to then be left with problems in your in your final expression with involving the trig functions that might involve double angles or things like that. One very important thing to keep in mind is that generally it's not okay to leave expressions that involve like sine of arcsine of stuff, or tangent of arcsecant of stuff. You can't do that. So either use the triangle to figure out what that is supposed to be in order to do the conversion. Don't just substitute inverse sine or inverse tangent or whatever for your theta. You have to figure out what that expression is going to simplify to. If you started out with an algebraic function, you need to end with an algebraic function, unless it is a bare arcsine or arctangent or something like that. But you do have to go back all the way. That's not considered fully simplified if you leave it like that. In some cases, particularly if you have to use double angle identities or power reducing identities, you will have to convert back using those double angle identities in reverse until you get back to a single theta. And again, depending on how many times you applied the power reducing identity in the first place, you may have to apply those double angle formulas, those identities, more than once as well. But you will always eventually have to get back to a theta so that you can use your triangle in order to simplify. Do not leave trig functions of inverse trig functions in your final expression. This is what the triangle is for. All right, so our last example is going to involve a secant substitution. And in this particular example, we're also going to illustrate the fact that it doesn't have to only just be square roots. It can be any half power that we can apply this to. So 3/2 powers, 5/2 powers, those are all fine. Because essentially they're all just the radicals with some power outside of them. All right, so rational exponents are just radicals in disguise. So here we have a function squared minus a constant. And so that's a secant substitution. That's the first thing that we identify. The second thing that we have to keep in mind is that this 7 is equal to a squared. And so the a that we're going to substitute is radical 7. And then our function here is just x. So we're going to replace x with the square root of 7 times secant theta. And the derivative of that is therefore radical 7 times secant theta tangent theta. And when we replace our secant into our radical expression here, this should reduce to the square root of 7 times tangent theta, because it's related with the Pythagorean identity. But let's walk through this and see if that actually happens. So here's our original problem. We're going to replace this x with our substitution, square root of 7 secant theta. Here, we're going to replace x with the square root of 7 secant theta, but we're squaring it. And so that becomes 7 secant squared minus 7. And then our derivative dx gets replaced with all of this from up here. Okay, so now best thing to do, pull out all of your constants. Now, the one that's under the radical, you have to work a little harder at, but this square root of 7 and this square root of 7 becomes 7. We've got our secant squared tangent. We'll come back to that. This, we've pulled out the 7. It's still under the radical at this moment, but to get our secant squared theta minus 1, we apply our Pythagorean identity to turn that into tangent squared. And then this 7 is raised to the 5/2 power. That's our 7 to the 5/2, which is 7 squared times radical 7. And then tangent squared to the 5/2 is, the 2's are going to cancel. We're going to get tangent to the 5th. And so I'm going to pull out these two constants outside. 49 times 7 is 343, and the radical 7. And I'm left with tangent to the 6th because I have tangents 5 and 1 there. And then secant squared I already had over here. Now I have even secants. So this is going to be my du. This is going to be my u. So I let u be tangent theta. Du is secant squared. So that goes away, and I'm left with u to the 6th with this crazy constant. Who cares? Raise that using the power rule. I'm going to get to divide by 7, which is going to cancel out one of those. U to the 7th. I put my u back, which was a tangent, but I'm not really done because I have to go back to my original substitution. So again, think about our original substitution. Let's go back up a little bit. It was this. That means that secant theta is x over radical 7. What is secant? It is hypotenuse over adjacent. Hypotenuse over adjacent. What is the remaining side? It's going to be that radical that was in our original problem. It's c squared minus a squared under the square root. So now if I want to think about my tangent is opposite over adjacent. So it is the square, the radical x squared minus 7 over radical 7. And all of that is raised to the 7th power. Well, this right here, this is a bunch of 7s, radical 7. This is 49 over radical 7 is 7 to the 5 halves. This is 7 in the denominator to the 7 halves power. And so that's going to leave all of these to be canceled, and then 2 7s under the radical left over. And the square root of 49 basically is 7. So that's that constant out front. And then the rest of this is just this square root to the 7th power gives me the 7 halves power. So again, use the triangle to get back if you need to. Often you can do these problems by just thinking about the radicals that you simplified in the original problem and your original substitution, but that isn't necessarily always going to work. And where it usually will you'll run into a problem is actually with the sines and the cosines, because that's where you use those power reducing identities. You get those double angle formulas, and then you get answers that involve both sine and cosine, and often to crazy powers. And the triangle will always get you sorted, even if you end up with some weird things going on, even if you end up with sine and cosine from a problem like this, the triangle will always get you sorted back to what you need in terms of the algebraic expressions that you started with.